And we are live again. Um, yeah. So haven't been stream. I didn't stream yesterday, if I remember correctly. Yeah. So I had like a rest day basically. But yeah. So welcome. Today we're gonna read a chapter mostly like a reading stream because I just need to the alcohols and their characters so I don't go lost in the exam. So, and I want to bring you along so we can learn it together and remember it also together so I don't get screwed. But yeah. So, oh yeah, we also got one subscriber. So that's very special. So this stream will be a one subscriber special. But yeah, I really appreciate the guy or the person who um subscribed. It really means a lot to me, and even though it's like only one subscriber, it feels like I got a million. So uh, it's incredible, honestly. But yeah, I hope you all having a good day, and yeah. So let us begin this. Um, Everything is working well. Hopefully, it doesn't lag as much. All right. So, okay. Naming and design. Oh, designating, nating alcohols. Okay. Yeah, I just like I had a lecture at 8 a.m. so my brain is fried up. But I have to get this chapter done. Okay. We saw how to name alcohols in chapter 5 when we learned the basic rules of nomenclature. In addition to the names, alcohols are also often classified into the following categories: primary, secondary, and tertiary. Alright. This designation scheme, primary, secondary, or tertiary, indicates the degree of substitution of the carbon atom bearing the OH called the alpha carbon. This will become important later in this chapter when we explore reaction of alcohols. Specifically, we will encounter reactions where the designation, primary, secondary, and tertiary, will affect the reaction outcome. So there's gonna be example and identify whether the following alcohol is a primary, secondary, or tertiary alcohol. So we can see here, it has two branches, like it has a carbon there, and so that's a secondary alcohol. Oh, it's also this area. So that's a secondary alcohol. Okay, so let's just do this quickly. This one is a tertiary alcohol. This one is primary alcohol. This one is also primary alcohol, and this one is a secondary alcohol. Done. An alcohol, by definition, will contain an OH group in its structure. Therefore, we expect hydrogen bonding to occur. Okay. Hydrogen bonding does not refer to a type of bond, even though it's called hydrogen bonding. This terminology is somewhat misleading. H bonding actually refers to a force of attraction between molecules, an intermolecular force. This attraction is temporary or fleeting in the liquid and gaseous states. As two alcohol molecules approach each other, they are momentarily attracted to one another. How romantic. At low enough temperatures, if the alcohol is solid, then these forces will actually hold together the alcohol molecules in a crystalline state. But in the liquid or gaseous state, the molecules are bouncing off each other and they are not perfectly held together. Why? The misleading terminology, H bonding, at some point during your high school studies, you were likely exposed to a model of the DNA helix, which looked like a twisted ladder. Yeah, I remember that. That twisted ladder is actually two very large molecules, each of which is like a piece of cooked spaghetti, twisted around each other. Each rung of the ladder is a hydrogen bonding interaction between the two molecules. Each individual H bond by itself will not be strong enough to hold the two large molecules together. However, the cumulative effect of understand why we call these interactions the rungs of the ladder hydrogen bonding. This also explains why it's so easy to unzip the helix. You might learn the structure of DNA in the end of your organic chemistry course. For now, we will be. Oh, okay. So decided to interrupt me. Blah blah blah. For now, we will be focused on problems that deal primarily with small molecules, and therefore, for our purposes, we will should think about H bonding as an interaction, a type of intermolecular force. For any given alcohol, the strength of the H bonding interactions will be greatly dependent on the concentration. For a concentrated alcohol, there will be a fairly decent amount of H bonding interaction at any given moment in time. However, if we dilute the alcohol in a solvent that cannot form hydrogen bonding interactions with alcohol, then the H bonding effect will be minimal. Okay, so this will be a concentrated, this will be a dilute. Alright. Now, consider diluting alcohol in a solvent that can form a hydrogen bonding interaction with the alcohol. For example, a solvent such as water. In such case, the interaction is indeed very strong. It is similar to the effect of having a concentrated alcohol. This explains why methanol is miscible with water. The term miscible means that methanol can be mixed with water. They will dissolve in each other in all proportions. What? Proportions. However, not all alcohols are miscible with water. In fact, just the very small alcohols, methanol, ethanol, and propanol, and tert-butanol, are miscible with water. To understand why, we must realize that every alcohol has two regions: a hydrophobic region, which is water, and the hydrophilic region, which does interact well with water. Okay, so we have a hydrophilic region and a hydrophobic region. Alright, in the case of methanol, the hydrophobic end of the molecule is fairly small. This is true even of ethanol and propanol, but an interesting thing happens when we look at 1-butanol. The hydrophobic end of the molecule is now large enough to prevent miscibility. Alright. Water and 1-butanol were mixed, but not in all proportions. That is, 1-butanol is considered to be soluble in water, rather than miscible. The term soluble means that only a certain volume of 1-butanol will dissolve in a specified amount of water at room temperature. As we consider an even larger hydrophobic region, solubility decreases and at room temperature. Alright. Here is a rule of thumb that can help us predict solubility. In order to have a high water solubility, there should be no more than 5 carbon atoms per OH group. A compound with 2 OH groups and 7 carbon atoms will be soluble in water. A compound with 1 OH group and 7 carbon atoms will not be soluble in water. There are, of course, many exceptions to this simplified rule of thumb, but the rule can be helpful whenever we need to make a quick quick prediction about the solubility of an alcohol. Okay, whether the following alcohol is soluble or insoluble in water. We can see that there's only one OH group and the rest is carbon, so it's not insoluble. Yeah, okay, so yeah. Predict whether each of the following alcohols is soluble or insoluble. This is soluble. This is soluble also, since it has two alcohol groups. This is insoluble, and this is also insoluble. Boom. I am on a roll right now. Give me a moment. Yeah, everything is working well. Okay, predicting relative acidity of alcohols. As we learned in chapter 3, in order to determine the relative acidity of a compound, we must carefully assess the stability of its conjugate base. For example, to determine how acidic this alcohol is, we have to remove the proton and assess the stability of the conjugate base. Okay. So whenever a question that asks for acidity of alcohol, we just remove the proton. When we draw the conjugate base of alcohol, we see that the negative charge is on an oxygen atom. This is much more stable than a negative charge on a nitrogen atom, but it's not as stable as a negative charge on a halogen. Okay, so increasing stability, the halogen is more stable than just the alkane. Okay, therefore, in terms of acidity, alcohols will lie somewhere between amines, and hydrogen halides. Yeah. So increasing acidity. Yeah. Okay. The pKa for most alcohols will fall in the range 15 to 18. Remember, a low pKa value means that a compound is fairly acidic, and a high pKa value means that it's not very acidic. Compare the following. Okay. Oh, damn. Okay, so. Alright. In chapter 3, we learned how to analyze the four factors that stabilize a negative charge, aureo. The I in aureo stood for induction. We saw that neighboring halogens can withdraw electron density and stabilize the negative charge. This is more stable than this. Okay, because fluorine can attract oxygen's electrons. Therefore, the presence of halogens can lower the pKa value of an alcohol to around 14. In other words, the presence of a halogen will make the compound more acidic. The following two compounds will provide an interesting comparison. Okay, so cyclohexanol is less acidic than the phenol. Okay, interesting. The pKa of cyclohexanol is 18, whereas the pKa of a phenol is 10. This means that phenol is 8 orders of magnitude more acidic than cyclohexanol. In other words, phenol is 100 million times more acidic than cyclohexanol. Why? Why is there such a huge difference? We can understand why cyclohexanol has a pKa of 18, because that is within the expected range of alcohol. Okay, 15 to 18. So the real question is, why is the pKa of phenol so low? Why is phenol so more acidic than a regular alcohol? To answer this question, we will use the R in aureo, resonance. to explain the acidity of phenol. Okay, so they remove the proton from the phenol, boom, and they do resonance. So this goes there, this goes there, okay. This goes there, this goes there. Alright. The conjugate base of phenol is stabilized by resonance. This explains why phenolic protons are more typical alcohol protons. Find the most acidic proton in the following compound. Okay. The two OH groups will certainly be the two acidic protons in the compound, but we must choose which proton is more acidic. We must begin by drawing the conjugate base in each case, and then we will compare the conjugate bases using our four factors, Oreo. Okay, so they remove the protons in each of the alcohol groups. In both cases, the negative charge is on the oxygen atom. So our first factor, Oreo, A in Oreo, does not help. Neither structure is stabilized by resonance, so our second factor, Oreo, R in Oreo, does not help. In this case, it is the third factor, induction, that indicates which structure is more stable. Both conjugate bases are stabilized by the electron withdrawing effects of the two fluorine atoms, but the more stable conjugate base is the one where the two fluorine are closer to the negatively charged oxygen atoms. This basically. Okay. Therefore, we can expect blah blah. Okay. For each of the compound. Okay, so. Okay. Now, preparing alcohols. Yeah, whatever. Preparing alcohols. Overview. We will learn many ways of making alcohols in this chapter. First, let's review the various reactions that we already have learned in previous chapters. All of these reactions can be used to produce alcohol. Okay, we have substitution, where we have SN2 substitution with this base. Okay, and also H2O doing a S1 substitution, but only when it's tertiary. Addition, okay, with acid, with boration, and with okay, boron. Yeah, okay. This one is anti-Markovnikov, so it goes to the less substituted area of the molecule. Just have to remember that. Before we can learn new methods of making alcohols, you must make sure that you remember the methods that we already have learned above. Yeah, okay. What reagents will you to accomplish the following transformations? This alcohol goes to the less substituted part of the molecule. Then I will use this one. So yeah, it also. In this case, H and OH are added across the pi bond in an anti-Markovnikov addition. No chiral centers were formed, so the stereochemical outcome is not relevant. We have only seen one way to achieve an anti-Markovnikov addition of water across a pi bond: hydroboration oxidation. Therefore, our answer is basically what I said. Okay, let's just do this then. What reagents would you use to accomplish each of the following transformation? Okay, so we have yeah, I will use SN1 and water for that, since it's gonna be a tertiary alcohol. I will use boration for this one. I will use brome to I will use Br2 and H2O, and I will use what the hell? I will use the acid one. This one. right? Yeah. All right. In this section, we will reduction process. In order to understand what the word reduction means, we must go back and review the oxidation states are. We will do that now. There are two methods for counting electrons, formal charge and oxidation state. These two counting methods actually represent two flip sides of the same coin. To calculate formal charge, we treat all bonds as covalent, regardless of whether they are not. Treat all electrons as being equally shared, all covalent bonds. Using this, okay, yep. When we treat all bonds as covalent, the carbon atom appears to have 4 electrons of its own. Carbon is supposed to have 4 valence electrons. When we compare how many electrons carbon actually has with the number of electrons it is supposed to have, we see that everything is just right in this case. It is supposed to have 4 valence electrons, and it's clearly using 4 valence electrons. Therefore, there is no formal charge. On the flip side, we will now calculate the oxidation state of the same carbon atom. To calculate the oxidation state of an atom, we treat all bonds as ionic, regardless whether they are not. Okay. For each bond with a more electronegative atom, for the CCl bond, chlorine is more electronegative, so chlorine gets both electrons. For each of the CH bonds, carbon is very slightly more electronegative than hydrogen, so carbon will get both electrons in each case. But for the CC bond, neither atom is more electronegative than the other, so we must place 1 electron on each carbon atom. Now, when we count the electrons, it appears as though the carbon atom is 5 electrons of its own. But we know that carbon is only supposed to have 4 valence electrons. This carbon atom is using 1 extra electron, and therefore this carbon atom will have an oxidation state of -1. Formal charges and oxidation states represent two different ways of estimating electron density. Neither method is perfectly accurate. Each method assumes an extreme that is not true. Formal charges are calculated based on the assumption that all bonds are covalent. Generally an incorrect assumption, and oxidation states are calculated based on the assumption that all bonds are ionic, generally an incorrect assumption. Earlier in this book, we focused our attention on formal charges exclusively. For purposes of this section, we will now focus our attention exclusively on oxidation states. Carbon can range in an oxidation state from -4 to +4. I already know. Yeah. Okay. Notice the trend. Let's ignore the two extremes above, alkane and carbon dioxide, and let's focus on the middle 3 compounds, alcohols, aldehydes, and carboxylic acids. Carboxylic acids are at higher oxidation state than aldehydes, which in turn are at a higher oxidation state than alcohols. Now imagine that we're running a reaction that converts an alcohol into an aldehyde or a carboxylic acid. This reaction will constitute an increase in oxidation state. Whenever we run a reaction that increases the oxidation state, we say that the oxidation has occurred. Therefore, converting a primary alcohol into aldehyde or a carboxylic acid is called an oxidation. Okay, so primary alcohol gets oxidized to aldehyde, gets oxidized to carboxylic acid. Similarly, it also called an oxidation when we convert a secondary alcohol into a ketone. Okay. In order to accomplish an oxidation, there's always some other compound that must itself get reduced. that compound is called the oxidizing agent because it causes the desired oxidation. Whenever we run a reaction that involves a decrease in oxidation state, we say that a reduction has occurred. For example, converting a ketone to alcohol. Yeah, okay. So basically, from a ketone to alcohol or aldehyde to an alcohol. Okay. Notice that the product of a reducing C double bond O bond is simply an alcohol. Therefore, we can make alcohols by reducing ketones or aldehydes. To accomplish this reduction, we will need a reducing agent. Okay, there are two common reagents for doing this. In order to understand the structure of these reagents, let's quickly review something from the periodic table. The elements boron and aluminum are in the same column of the periodic table. Each of these elements, boron and aluminum, has 3 valence electrons. Therefore, each of these elements can form 3 bonds. Okay. In the compounds shown above, boron and aluminum are using their valence electrons to form bonds. But notice that neither one has an octet. Each element is capable of forming a full bond in order to obtain an octet, but then each element will bear a formal charge of -1. Interesting. Sodium borohydride and lithium aluminum hydride. Okay. In both of these compounds, the central atom, B or Al, has 4 bonds and a negative charge. In the first compound, NaBH4, or sodium borohydride, sodium is used as a counter ion. In the second compound, lithium aluminum hydride, lithium is used as the counter ion. The choice of a counter ion is usually not relevant for our discussion, and we will choose to ignore it from now on. Okay, fine. Either one of these reagents, sodium borohydride or lithium aluminum hydride, can attack a ketone or aldehyde to give an alcohol. So those two are basically reducing agents that I have to remember. Okay, so okay, so I can use both with water and this with methanol. Okay. The mechanism is somewhat complex and beyond our scope of the course, but the following simplified mechanism will be useful. So this reacts this under the octavolute, this goes up there. This has an empty, yeah, this is that's pretty simple, fine. As we carefully analyze the first step of the mechanism, we see that a reducing agent, lithium aluminum hydride, is simply functioning as a source of H-. The mechanism of the first step is same whether we use lithium aluminum hydride or sodium borohydride. Then in the second step, a proton source is used to generate the alcohol. Okay, that's pretty easy. So when we have to get an alcohol from a ketone, we have to use lithium aluminum hydride or sodium borohydride. Okay, I have to remember that. That's pretty easy to remember, right? Can't be that bad. Okay, so Let me see here. Let me see here. We have now seen the way that lithium aluminum hydride and sodium borohydride work. Essentially, they are both just sources of nucleophilic H minus. You might wonder why we can't just use sodium hydride in a sodium. Yeah, okay, like this. What? Okay. Okay, I'm not reading that. The proton source water is the proton source water is introduced into the reaction flash only after lithium aluminum hydride has finished reacting with the ketone. The proton source methanol is present during the reaction. Okay, so I have to remember this is two separate steps and this is one step. Okay. Notice that with lithium aluminum hydride, two separate steps are required. So far, we have seen two sources of nucleophilic H minus lithium aluminum. Yeah, okay. There are many other hydride reagents that we have been prepared. Some that are even more reactive than lithium aluminum hydride, and others really. For example, where? Oh, okay. By choosing the R groups above to be either electron donating groups or electron withdrawing groups, we can carefully control the reactivity of the hydride agent. For now, we will focus our attention on the two commonly used hydrogen reagents. These two we just learned. Let's do some problems. Okay, let's do some problems. Identify a ketone or any other reagent you will use to prepare fluorine alcohol. Yeah, so this should just be a ketone. And then I will use this one with water. Boom. Or this one. Okay. Okay, identify the... Bro. That's pretty easy. See, that's the ketone right there. Aldehyde, ketone, ketone, aldehyde, aldehyde. And then you just use these lithium aluminum hydride or sodium borohydride. Boom. With you use lithium aluminum hydride with water, and those are two separate steps. And you use sodium borohydride and methanol as a singular step. Boom. Fine. Okay. I can remember that very good now. Preparing alcohols via Grignard Grignard reactions. In the previous section, we saw that ketones and aldehydes can be attacked by suitable source of H- in a similar way. Ketones and aldehydes can also be attacked by suitable source of R-. Compare these two reactions. Okay. Yeah, okay. Both H- and R- can attack a ketone or aldehyde to give an alcohol. The main difference is the effect of the carbon skeleton. With H-, the carbon skeleton does not change at all. But with R-, the carbon skeleton gets larger, we are forming... Wait, what? Oh, yeah, that's right. Yeah. We are forming a CC bond. We will soon see that this is very important for synthesis problems. For now, let's focus on how we can make R- in the first place. After all, a negative charge on a carbon atom is not very stable, and therefore not trivial to make. There are many ways to get a negative charge on a carbon atom. Later on this course, you will spend more... Yeah, I heard about Grignard reagent, actually. Where the R is an alkyl group, in a Grignard reagent, there is a carbon atom that is directly connected to a magnesium atom. If we compare the electronegativity values of C and Mg, or carbon and magnesium, we will see that carbon is more electronegative than magnesium. Therefore, carbon pulls more strongly on the electron density and will develop a negative charge. Grignard reagents are formed by inserting magnesium in between a CX bond where X is a halogen. Alrighty. So kind of yeah, the mechanism for this insertion of magnesium is beyond the scope of course, and therefore we will not go into it. Actually, how does it like connect to have people found out that how the mechanism really is? That's interesting. For now, we will should just know that we can insert magnesium into a CX bond where X is a halogen. Here's some examples. Yep. Okay. Okay. Once the magnesium atom is inserted between the CX bond, the newly formed C magnesium bond is somewhat ionic in the character because carbon is much more electronegative than magnesium. Therefore, there are two acceptable ways to draw a Grignard reagent. Okay. Neither drawing is absolutely correct. The first drawing assumes a perfectly covalent bond, which is certainly not accurate. The second drawing assumes an ionic bond. The reality actually lies somewhere in between those extremes, although it is closer to being ionic. When a Grignard reagent attacks a ketone or aldehyde, it forms alcohol. With a new with, with a new with a newly installed R group. Okay. So a ketone when the Grignard reagent is there, it gets installed and then it creates alcohols. Here are two examples. Okay, I see. Okay, I see it. Yeah. Yeah, okay, I see. This is just a methyl group and then it gets okay. Yeah. Yep. Okay, that's not that bad on it, honestly. Grignard reagents also attack other compounds possessing a C double bond O bond, such as esters, to produce alcohols. For now, let's just focus on Grignard reagents attacking ketones and aldehydes. Show how you would use a Grignard reaction to prepare following. Okay, this one should just be a ketone without this one. Boom. And then, yeah, methyl. Yeah. Yep. Yep. Yeah. I get it now. In this section, we will learn that the Grignard reagent can attack ketone or aldehyde to give an alcohol. This reaction is so incredibly important because we are not only converting a ketone into an alcohol, but we also introducing an R group in the compound. Okay, so with the Grignard reaction, you can also make an alcohol. That's all I have to remember. Fine. Yep. Summary of methane of preparing alcohols. So far, we have seen many ways to make alcohols. We make primary, secondary, tertiary alcohol through various methods. As review, identify. Mm, 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 mm. Yeah. So yeah. Yeah. Okay. In this, okay, reactions of alcohols, substitution and elimination. Now that we've seen how to make alcohols, we will focus our attention on reaction of alcohols. Let's start by reviewing a reaction that we already seen, substitution and elimination. Let's begin our review with elimination reactions first. We have seen two types of elimination reaction, E1 and E2. To eliminate the OH group under E1 condition, we need acidic concentrations. Okay, so when I see this in the exam, it's E1. Alrighty. In this reaction, the acidic conditions are used in order to protonate the OH group, effectively converting the OH group into an excellent leaving group. And then the leaving group leaves to give an intermediate carbocation, which then loses a proton to give the alkene. For review of okay, because the E1 mechanism involves an intermediate carbocation, this reaction works well with the tertiary alcohol, although it can also be achieved with secondary alcohols. For primary alcohols, we will not be able to form a carbocation. Therefore, we will generally cannot use an E1 reaction on primary alcohols. Instead, we will use an E2 reaction, but we will still have the same problem. OH is still a terrible leaving group. That problem was resolved in an E1 reaction because the OH group is protonated under strongly acidic conditions, thereby converting a bad leaving group into a good leaving group. In the E2 reaction, we will also need to convert the OH group into a better leaving group, but we cannot use a strong acid because that will be incompatible with the strongly basic conditions that are required in order to perform an E2 process. Therefore, we want to use E2 conditions. Therefore, if we want to use E2 conditions, we will first need to convert the OH group into a tosylate group. Okay, so they use tosylate, and then you can. Oh, okay. Holy hell! Yeah, okay. Okay, they use zinc, apparently. Alright. Alright. To oxidize alcohol, we use chromic acid, sodium dichromate, and sulfuric acid. Okay, chromic acid goes all the way to carboxylic acid. What if I want a key? PCC. Gotta remember. Okay, PCC. PCC for oxidizing. Yes, and just it's or aldehyde. Yeah, PCC, sodium chromate, something, sodium dichromate, lithium aluminum hydride, and water. The same again, and PCC. So, uh, the reducing agents to reduce an ketone to an alcohol is lithium aluminum hydride and water. It's two separate steps, and was it sodium borohydride? Yeah, sodium borohydride, and then with methanol. And for oxidation, we have PCC that oxidized to an alcohol, to an aldehyde, or a ketone, but not a carboxylic acid. We have to use sodium dichromate to oxidize it to carboxylic acid. Grignard, like Grignard reactions makes an alcohol also, but with the new installed R group. That is basically what I need to remember for my exam, or else I will be finished. So yeah, that's pretty much. That was a bit revising. I mean, now I will be doing some mathematics, since my math exam is what, 2 days. Yeah, actually 2 days. Oh my god. Yeah, so my math exam is in 2 days, so I'm just gonna do some math exam sets, I guess. Yeah, best I do that now so I don't regret it, and then we are allowed to have notes in the exam. So I just need to print that shit out, and yeah. Yeah, so I'm gonna do some math. Mm. Yeah, so I can't share my screen for some reason. It still annoys me. But yeah, I'm gonna end the stream now so I can focus on math. Just gonna uh was gonna do this small reading stream just to uh remember shit with you guys. So yeah, hopefully you also learn something how to oxidize and reduce or make alcohols now. And yeah, so how many days is it? My exam is was it 3 days? Yeah, if my computer likes to respond. Yeah, 3 days, but counting this is 4. So yeah, I hopefully I will make it. Honestly.